And also before I begin, I also want to really say my gratitude both to Professor Denise Duarte and her team who supported me the whole week. It is Luciana Schwanger Ferreira and Paula Shinzato, and as well as Carolina dos Santos Guzon. Thank you very much for having me, and I'm really grateful for the opportunity to be here, to experience this work group, and to collaborate together with you. So let's talk about development and evaluation of urban heat island mitigation strategies using simulation approaches. In the beginning, I just want to very quickly go into the motivation. And as I, of course, have some kind of expert audience today, I just want to quickly say something about urban heat island. So as you all know, it is a island-shaped, warmer place that is surrounded by cooler rural areas. And we have large gradients of air temperature between the urban and the rural area. It can be around 4 Kelvin per kilometer, so it is quite a lot. And when we look at mitigation strategies, we first have to look at what are the influences of the urban heat island onto the meteorological, onto the economic, and maybe also on the biological spheres. So it has, of course, an increased demand for cooling energy. So if it's very hot outside, we need to cool down our inside, maybe via natural ventilation, but also maybe via AC, via air conditioning. And this again, if we're using air conditioning, we also increase our electricity. So our electricity has to be generated somehow. This again leads to higher emissions. And I think you already start to see this vicious circle that is coming here. Then, of course, we have also very interesting effects, quite recent research about urban area inducing rainfalls. And this is something, okay, why not? Rainfall might not be too bad, but a rainfall in a city with so much impervious area, so much impervious surface, can mean something really bad, because the water is not retained, it is not a buffer. If we have lots of natural soil, the water has been retained in the soil is slowly keeping it and making it available again to the vegetation. But in cities with all the impervious area, you have a lot of surface runoff, and then the canalization is getting a lot of load, yeah, in a short period of time, because you don't have buffers like natural soils. And of course, you also have increased biogenic emissions of volatile organic compound. What I want to say with this is the vegetation we have in the city, it has been evolved over millennia of years, millions of years, and it's not used to live in a city in this specific environment. But it has to cope with it. We plant it there and we expect some kind of benefit from it. We want it to cool down the atmosphere. We want it to have a positive effect of the atmosphere on our thermal comfort. But some of the plants, they don't like it there very much. So they they are stressed. So they emit some kind of gases in order to protect themselves. And these gases can often be precursor gases, especially in the case of isoprene, that can lead to very harmful construction of tropospheric ozone, so O3. Yeah? And you see that a lot in summertime when there's lots of, or here maybe in wintertime, when you have lots of clear summer days. With all the solar radiation coming in, you have lots of production of O3 in the city. So even if we say, okay, vegetation, we know one mitigation strategy already, vegetation, we have to carefully think about what kind of vegetation, in which sense do we implement the vegetation. And of course, a city is not equal to any other city. So Sao Paulo is very different from, of course, my hometown, Mainz, but it's also very different from other cities within Brazil. This is the approach of microclimate. We do not have easy solutions for a complex problem, and we need to account for that, of course. So let's have a look onto the meteorological scales. We of course have the macro scale. Yeah? In the macro scale you have all these different phenomenons like El Nino. You also have really global warming is of course, global warming is on the macro scale. And then you have, of course, mesoscale features such as the effect of terrain, maybe, the effect of large forests, the effect of metropolitan areas such as, huge metropolitan areas such as Sao Paulo. And you have the microscale. And you might think, okay, the microscale is dwarfed by the others. These are very dominant and the microscale is dwarfed. Well, I propose, well, it's not really like this. We live in the microscale, yeah? These are also interfere with us. But most of the time, it makes a big difference. Am I standing beneath a tree or am I standing directly in the sun? So the microscale is the place where we live. And the microscale is also the only place where we can make a difference towards global climate change. Yeah? If we do we cannot implement something on a macro scale easily. We cannot cool down all the oceans immediately. We don't have this kind of technology. Maybe you've heard of some proposals to put huge mirrors in space. Yeah? This is something, it sounds a bit futuristic, it sounds science fiction, is of course very dangerous. Yeah? There's been some articles recently about this. So currently we don't have the technology to interfere with these scales, but we all have the chance to interfere with this space, to change the microclimate differently, to shape a better microclimate in our city quarters, and this then goes back to the mesoscale because it changes the city quarter, and if you have many city quarters that have a better microclimate, then we have a mesoscale feature. And if we have fixed a lot of problems on the mesoscale, it will propagate back to the macroscale. So we really have to think of the microscale, do not get maybe turned down by the word micro. It doesn't mean it is micro important. It is macro important, but micro only in scale of dimensions. So I want to quickly talk about a microclimate model that I'm part of the development team. And it is called ENVI-met, Environment Meteorology. And you see a model area here. And it is basically a bit like Minecraft. You can think of it like Minecraft. You discretize the space in blocks. Yeah? These blocks can have different resolutions, maybe 2 by 2 by 2 meters, and then they can either be part of the atmosphere or part of a building or part of the vegetation, etc. And you're able to replicate your model or your city quite accurately. And then the model is given some boundary conditions. Maybe you want to simulate a hot summer day or something like this. And then the model will give you some prognostic output. It will tell you, okay, given this input and given the configuration inside your model area, you will see distributions of wind speeds, temperature, humidity, turbulence, other scalars, etc. And in order to simulate very accurately, you cannot only simulate the atmosphere, because microclimates happens because of the interactions between different objects, between the atmosphere and maybe the surfaces, the ground surface, between atmosphere and also the building surfaces, and of course between atmosphere and vegetation. So in order to accurately replicate all these different features, to accurately model the microclimate in an urban area, you have to be able to accurately simulate the processes of vegetation, that being the leaf temperature, the energy balance of the leaf temperature. You have to simulate the evaporation, the transpiration. So you need to know, okay, a tree is not something static, it reacts to the environment. So when it's too hot, then it closes its stomata, that meaning it closes the small openings on the bottom side of a leaf, letting out less water. Yeah. Also it reacts, of course, also to the soil. So if there was no rain for a long period of time, the soil gets drier because the vegetation is sucking out water out of the soil. But at some point we don't have a replenishment because rain is maybe lacking. And then the soil gets dry and the vegetation cannot fulfill all its beneficial effects anymore. And of course, something that is very important is the interactions between buildings and atmosphere. So having a very accurate representation regarding the reflection, maybe of glass facades, or also the heat storage that has been released, especially at nighttime, in the building loads. That all the energy that is stored during the day in the buildings, that of course has to be modeled quite accurately. And before I get into two mitigation measures that I want to talk about, and this is also something for a go-home message, it's something to think about, okay, how can we improve this? I want to quickly talk about typical applications. So what do? We typically have a model area where we're interested in seeing some effects in the outdoor determined by changes. For example, we have a park here, and we want to know, okay, if I have this park, or if I reduce the size of the park or increase the size of the park, what is the immediate effect onto the environment? And then we can have something like this. We can have a look at the air temperature at 4 p.m. and you will clearly see inside the park you have lower air temperatures, and then on the sealed surfaces close to the buildings, maybe south-facing facades. This is in Essen. It's a city in Germany. So the south-facing facades are, of course, hotter than the north-facing facades because they are direct into the sun. You see hotter air temperature. Yeah. So this is a very classical thing. You can also have a look at what is now a very hot topic is the particulate matter and also the tropospheric ozone. So that comes, of course, from combustion processes. So you digitize cars driving along, and every individual car, you say, okay, this car is a diesel engine car and it's emitting X amount of particulate matter, X amount of NO and NOx. And so you see, okay, what is the result of this, the effect of these cars onto the air pollution. The air quality is more and more an important topic that comes into the microclimate as an additional feature that we cannot ignore. And there's another typical application, and this would be, you would not be so much on the outside of the, interested for the outside, but you're more interested for the building envelope, the building physics. And this would be that you really, with a high resolution, digitize your buildings. This is a test area of the Fraunhofer Institute in Holzkirchen, and you will see something about this in a second again. What do we want to analyze here? So you maybe have a small model area where you have individual facade elements like glass and then concrete. This is a lighter concrete, a denser concrete, and inside these buildings, you said, okay, it's different flats. Yeah. So this first floor, this third floor is separated in two flats. The second floor, the first floor too. There are two flats inside, so there are distinct air volumes inside it. And when you then simulate, you can first maybe have a look at the outdoor facade. And having a look at the outdoor facade, you see, okay, was a tree in front. Yeah, there's a tree in front of this building. You can clearly see its effect. Yeah. So the solar radiation is being attenuated by the tree, and you see that the less solar radiation is reached to the facade, is reaching the facade, so the surface temperature is lower. And then you also have the indoor air temperature, an approximation of the same, and you see all of these individual flats. They carry a different indoor air temperature because they get different amount of energy and react differently to it. Okay. So let's come to these mitigation measures. So the mitigation measures I want to talk about are basically two things. And I think these are the two most dominant objects in the city. When you think about city, you think about buildings. Yeah? City is mostly composed out of buildings. And when you think about city in the sense of urban heat island mitigation, you think about vegetation. And these two things, they should be modeled quite accurately in order to quantify how much can I change, can I shape, can I better the urban microclimate. And in the first part, I want to talk about the building models or buildings and their role in the urban environment. And then I want to speak about building atmosphere interaction and go into proportion where I say, okay, building performance simulations like Energy Plus, like Trinsis, etc. How can we improve them by adding the microclimate, the local microclimate to them, in order to then improve the outdoor and indoor climate efficiently? And in the second part, I want to go into urban vegetation and show you, okay, a tree being not a static object in our environment, how is this shaping the microclimate, and how can we model it accurately in order to give guidelines? Because if you look at urban planning is complex. Yeah, you cannot give them 1,000 numbers, a huge Excel sheet or something. It should be clear guidelines on what to do and what not to do. So we need to model the differences in reaction of different trees quite accurately, and I also want to go into something quite recent that is very important, of course, when you do not have a lot of space, because a tree vegetation will take up a lot of space, of course. So what about rooftop and facade greening? Yeah? What are the options here? So let's first with the building models. Yeah? The building models. Buildings shape the atmosphere. This is clear to us. Yeah? Buildings, they interfere with the wind field, they interfere with the energy balance, and they of course interfere with the shading. The lowest daytime UTCI or PET values, or maybe TEP values, you will see in the shade of buildings because they cast a very, very thick shade, a very dense shade. And buildings, of course, shape the atmosphere, but what about the other way around? Yes, it also works. So it is an interaction. It is atmosphere also shapes buildings, yeah, the building performance. The indoor temperature strongly depends on the atmosphere. The energy consumption, AC, in the summer, or maybe heating, not so much here, but in our latitudes, heating is very important. Energy consumption is, of course, being shaped by the atmosphere and the properties of the same. And then, of course, comes something very important, cost. Most people, it's hard to explain these things to them, and it's even harder to explain these things to them, yeah, as they are physical parameters, but costs everybody understands. So simulating costs is something really important if you want to change, if you want to better the environment, because if you can express something in money terms, everybody will understand it, and everybody will agree, okay, we have to save money, yeah? Because we have more money for other things. Okay, so I want to also talk about building performance simulations. Why do I think that building performance simulations need improvement? Well, I think building performance simulations are a great tool, don't get me wrong. They are really, really good in approximating building energy consumption and the effects of building-related measures, such as more insulation, less insulation, and other effects, maybe natural ventilation, etc. So they are a really great tool, and we should use it. We should use it a lot. But I say that they are very insufficient into taking into account the actual local microclimate conditions. So what you usually do, you take some weather file, a year-long weather file, an EPW file maybe from Energy Plus, yeah, Energy Plus weather file. So you have hourly values for a location, maybe Sao Paulo, yeah, or maybe another place. And this exact file, you run a simulation of building performance simulation with. But something is a bit weird. It sounds very easy, and this should make us think, why is it so easy? Is it that easy? No, I don't think it is. Because in these Energy Plus weather files, you have no distinction about where your building is placed. You only have your building, and then the atmosphere coming from this static file, one file for Sao Paulo. Sao Paulo has many different microclimates. Why do I only have one file? It is not taken into account that maybe there are other buildings really close by, that there is a park next to it, there are many trees next to it. This is not in there. So we need to improve there. And of course, if we have all these information, if we had all this information, then we could go back again. Okay, maybe I don't need my AC that much. Maybe I can skip some of the insulation. Maybe I can use less reflective or more reflective surfaces. So this, again, has also interference with the outdoor. So, like I said, building models are great. They have a high-resolution wall structure. They have definition of sections of rooms. Where is a heater placed? Where is this placed? Inside circulation, and so on. And using these year-long simulation files that are often test reference years or reanalysis data, they are able to run for 1 year. But, like I said, they do not account for the local microclimate, but rather a general mesoscale condition. Let's have an example. So this is the map of Germany. You all, I think, know Frankfurt. Yeah, it's the financial center of Germany. Yeah, all the banks are situated there. And then there is, here you see Luxembourg, Belgium, etc. So I'm not just arguing, my city is, by the way, here, it's Mainz. It's not a small city, it has 200,000, for German standards, it's not a small city, 200,000 inhabitants, yeah? And it doesn't have a blue spot. Yeah, so we don't have data there, not for a year-long hour resolution. And I'm not saying that this is a problem. I think it is a problem, yeah? But the problem that we have only one blue dot for Frankfurt, that you have only one blue dot for Sao Paulo, it's an even bigger problem. Because the really local effects are not in this single file. So what do I want to do? What is something, I gave you a lot of problems now, but what could be one possible solution? Well, I want us all to think about, what about using a microclimate model that is running using the EPW file, the blue dot data that now incorporates the mesoscale, the general conditions, and you run a model area with a microclimate model, and then you use the simulation results of the microclimate model and extract all the data of the building on an envelope, the building that you want to simulate in the building performance model, and put it inside Energy Plus, Trinsis, etc. This would be a much better approach. And it would lead to an urbanization of the input data, or maybe a localization of the input data. It's not just generic data any longer, but it's really the data in front of your facade. And not just in front of the south, east, west facing facade, but in front of every individual facade element that you simulated. So it's different in the lower left corner of the building than the upper right, and maybe the next 2 meters is very different again because there might be shade from a tree that is situated next by, etc., etc. So it would look like this. You have this model area maybe, yeah. You run this in ENVI-met, yeah. And then you have this building is the one that you are simulating in Energy Plus, that you want to simulate in Energy Plus. But before doing so, you extract for every facade element. So from this, you extract the long wave radiation received. You extract the direct radiation, shortwave direct, shortwave diffuse radiation, the wind speed, the air temperature, the humidity, all the different parameters you need as boundary conditions for Energy Plus. So that sounds simple. Why isn't it been done? Yeah. What is so difficult about this approach? Well, it's two things. Two things are quite difficult. First, to be able to extract this data and then use it in a BPS model, you have to simulate the facade, the interactions between the facade and the boundary layer of air right in front very accurately already. Because if I want to use maybe the air temperature as boundary conditions for the BPS, then I would already have to simulate accurately inside the microclimate model, because it is the data that I want to use further to run. So if my facade temperature in ENVI-met is wrong, yeah, then the air temperature in front of my building is wrong. And this is the data I put into Energy Plus, so I won nothing. Yeah, I just wasted a lot of time. So this is something that I first have to do. I first have to ensure that the facade temperature coming from ENVI-met is very, very accurate, so that the atmospheric parameters in front of the facade are also very accurate. And then second, we have a very big difference in scale and in numerical computation time. So a micro model, they are very computational heavy. To run a 24-hour simulation, it usually takes 24 hours. And if it's high resolution, like lower than 2 meters of every grid cell. Yeah? So in order to get a year-long data, you would first invest 1 year. Yeah? So this is not something, it's not viable. But what you can do is you can interpolate mean atmospheric conditions or use maybe multiple nesting. What do I mean with this? Well, you have maybe a whole year, but many days are similar to each other. Yeah? I've been here for 1 week, so I'd say Sunday, Monday, Tuesday, and Wednesday. They were very similar. Yeah? All of the days were no clouds at all. We had almost the same amplitude in temperature and humidity, and also the wind speed was very, very similar. So do I really need to simulate 4 days, but they are the same? No, I don't. Yeah. So before I run a whole year simulation, I make a statistical approach. Yeah, I make a statistical approach and only catch the specific days that are very significant for my location, and then I only run them. And I can run them maybe quicker if I use a coarser resolution using multiple nesting. So I don't run the high resolution alone, but maybe I run a coarser resolution, maybe with 5 meters or 10 meters resolution before, and then use this data to approximate and see how big, how fine do I have to go with my grid. So these are possibilities to overcome this problem. First, let's see how we overcame this here. And then secondly, I show you some approaches here, and this is something that we are currently working on, because it's not simple, yeah? And you have to do the statistical approach for every city, because here there might be 8 or maybe 30 days like Sunday to Wednesday, but in other places there are more or less. So let's first talk about how can we accurately simulate facade structures and facade temperatures outside, and then the air temperature in front too. So ENVI-met has a multiple node model. So while maybe building performance simulations have 100 nodes, we have only 7. But our focus is more on the outdoors, so this justifies the matter. So we build our walls out of 3 different materials, and the model can be run in 2 modes. You can have the indoor temperature as a prognostic parameter, meaning it changes over time. This would be that you do not have an air condition, so you have no regulation. Or you can run it constant, that you say, okay, my indoor temperature is always 20 degrees centigrade, and then you would get an idea, okay, how much energy was needed to keep it constant. Yeah? And you, of course, have the energy balances that are being used. I do not want to go into them. I just want to show you some results, and these results were undertaken using measurements. Yeah, so we are always happy because we come from the modeling side, but modeling without reference is something doesn't make sense. So we need people. We need also people, and I'm very happy to have these partners here in Sao Paulo who do a lot of measurement. That we get measurement data and then evaluate our model. And in this case, we had measurement data from the Fraunhofer Institute for Building Physics. And they operate a testing site, a huge testing site for building materials, where they continuously measure the facade temperatures and also inside the building. And they also have all the data of the meteorology outside, yeah, that we can also recreate the specific day in the model. So this is what the testing site looks like, and we picked out this building and simulated a complex structure. So there's an uninsulated facade at the bottom, an insulated facade at the top, and here is a measurement sensor for the facade temperature. So let's have a look at the results. What you see here is the solid lines, yeah, they are the measurement data, and the dashed lines are the simulated data, and the gray one is the difference. And you see some statistical values up here, the root mean square error and the R square. And what you can see is that the model really accurately is able to replicate the facade temperature. So this made us very happy, yeah? Because it means, okay, we can go on and use the atmospheric data in front of the facade in order then to go forward with the coupling of building performance simulations. So now the downscaling for ENVI-met to BPS models. So we did exactly this. We have simulated this area and then took out the building envelope for every facade element. And what I'm showing you in the next slide is what would the air temperature look like if I only used energy plus data versus I use a coupled approach. And the coupled approach, if I showed you for every facade element a line, yeah, you would have a lot of lines in this graph. So I averaged them for the east, west, south, and north facing facades. Yeah? And you don't see in the air temperature as per se, but you see this would be 0%, it's the reference, it's the energy plus, what energy plus predicts. And the difference from energy plus to energy plus is, of course, 0. And you see in percent the differences in air temperature for all the different facade elements. And you see it's quite significant. Yeah? So it makes a big difference for the air, just the air temperature. And the air temperature is not the most important thing. I suspect the radiation is even much, much more important, especially at nighttime, maybe the long-wave radiation that has been reflected from facade to facade. Let's have a look at the wind speed. So the wind speed, are now absolute values. Black, again, is the wind speed from energy plus. So what is, during the period, what would energy plus put on the wind speed onto the building? Yeah. Well, it's quite high. Of course it's quite high because the reference stations, yeah, the reference locations for the Energy Plus weather files, they are often outside the city. Yeah? They do not take into account all the displacement height or the roughness of the city. So ours are much lower and they are of course much different. Yeah? This is in the downwind, yeah? Downwind facade. You have much lower wind speeds. So the sensible heat flux is of course very, very different. This, of course, is important for the building. Yeah. Okay, let's come to a short conclusion before I go to the vegetation quickly. Yeah. So we have a successful introduction of the multiple node model, and we could show that coupling simulations we only did it until now for a short period of time, maybe 10 days or something. Yeah. It showed good effects. It showed significant improvement for the BPS model. And the future tasks are the ones that I told you about, yeah? And we have to think about this, and I'm happy if I get maybe some feedback from you, if you have some ideas how to do it properly, how to do a statistical analysis to separate some days that are very similar and then only model them. And we are thinking about cluster analysis, machine learning approaches, k-means, etc., k-forest approaches, and then quantify the effects of the heat mitigation strategies onto building energy consumption and vice versa. Okay, that was quite long. I'm sorry for it. Let's go quickly, I promise, into the urban vegetation. Yeah? And what can we do there? So we all know effects of trees are very important. So first I want to show you, okay, how can we model trees accurately and what guidelines can we deduce from the results? And then I want to show you some results of some work that we're currently doing in a science project, in a research project together with the EU. So first, vegetation is also a very important factor on urban areas. And this is the latent heat flux, of course, water retention, shading is important. And these are the effects onto the atmosphere, but also different than buildings. You see this is a bit brown now. And it's a bit brown because maybe this tree is not able to survive in this place. Especially for trees that are planted newly, they are not getting planted when they're already 20 meters big. They are planted when they're small. And small trees do not have huge roots. Small trees do not have a huge canopy. And because they don't have a huge canopy, they are susceptible to lots of heat, too much heat maybe, and they cannot survive. So this is a dilemma. We cannot plant big trees immediately, but we need trees to survive, and the small trees might die more quickly. And trees are a huge investment. This is something that has not been looked upon. Only very recently people understand, urban planners understand maybe that trees are a huge investment. It's that you plant them today, and they should live maybe for 80, 100 years. Yeah? So planting them today in the right spot, the right tree, and that is possibly to survive, it makes sense to first do analysis, not just plant it and see if it survives. Yeah. So we also have this relation. Vegetation shapes the microclimate, and this is something that has been going on in research a lot. Yeah, you often have research about how does vegetation shape the microclimate, but we also have to do the other way around. Can this vegetation live in the microclimate? How is the microclimate determining the health of the vegetation? Yeah, something that we have to have a look on. So a tree is very complex. I do not want to get into all of these bubbles here, but just to simulate how the stomata, how these openings on the bottom side of leaves that regulate the carbon intake for the photosynthesis and the water coming out for the transpiration process, exactly what we want, how is it regulated by the tree? Well, it's very complex. So it has a lot of biological stuff in there, like the respiration, the photosynthetic active radiation, the carbon isotopes that the plant is fixating. And it also have, of course, lots of meteorological parameters. And combining this is the challenge. Yeah? Understanding parts of the biology, understanding parts of the meteorology, and putting them together. And also, we need to think of plants as organisms, yeah? And this is something that we are guilty of as developers of ENVI-met. Yeah? For years, we thought of plants as, okay, they are individual LAD cells, yeah, leaf area density cells. We just place them three-dimensional in our model, and they don't communicate with each other. This is wrong. A plant, it communicates. This leaf cell is communicating with this. It is an organism, yeah? And it's working together. And if the top here feels bad, the bottom will notice. If the soil is getting dry, the whole system will notice. Yeah? So understanding it as an organism was the first step in order to improve. And in order to then evaluate our improvement, our remodeling, we had some measurements done. And we evaluated 2 plane trees. So this is in the city of Mainz, in a courtyard. 2 different London plane trees. They are very common in Europe. They are deciduous trees, not like the evergreens you have here. And they are different in size. And we had to take a courtyard, so it's the middle in the city center. It's a courtyard because there's, of course, lots of vandalism. So when people are very happy late in the evening or something in the city and they see some kind of measurement instrument, it might get destroyed. Yeah? And this is something you have to take care of, so we are using measurement inside a courtyard. And then we remodeled this courtyard and reassembled the trees. Here you see this is Mainz, yeah. This is part of a different city, and they are situated here, so close to one of the biggest rivers of Europe. Yeah, it's the Rhine River, and it is our study site. So you see it again in 3D here, just to get an idea how does it look. And what did we measure? Well, we measured 2 things on the trees. So first of all, we wanted to know, okay, how much water is going up the stem. And you can do this with a measurement instrument, with a sap flow measurement, where you have a heated needle drilled into the tree. The tree will not be harmed by this, yeah? So don't worry about the tree, it's fine. Yeah? So there's a heated needle in the middle, and there are temperature sensors above and below. And if there is lots of water coming up, the water takes the heat with it. So the topmost temperature sensor, it notices an increase in temperature. And from this increase in temperature, you can deduce how much water has been flowing up the stem. And at nighttime, it often happens the stem refilling, where the plants stop their photosynthesis, they start the respiration, so you have water coming down the stem maybe. Yeah? And then the second thing is we installed a thermal camera to measure the leaf temperature, to continuously measure the leaf temperature. And we built this ourselves. We're using lots of Arduino technology. I heard a lot about this here too already, so I'm really pleased about this. And I think these are great projects to build something, to do it yourself, and just create it in order to use it for continuous measurement, very cheap. So it is continuously measuring the leaf temperature of the trees. Now, we also, of course, need the meteorological data. We have the air temperature, humidity, wind speed, and wind direction, the radiation split into these different components. And we measured, like I said, the vegetation data. Now look at the results. So this is the result for the transpiration. Again, solid measurement, dashed is model. And on top you see the small tree, and on the bottom you see the large tree. And we measured because plants are very, very, for plants it's very important, the transpiration process, how much radiation is there. Yeah? So we have different cloud scenarios. So we have a clear sky period, a slightly cloudy, a mostly cloudy, and a fully cloudy scenario. And again, you see the statistical values underneath. You see it's very resembled very well. The short-term variations, everything is, we are very happy about this. But we were not very happy about this here. Yeah? And in the model, the small tree showed signs, it's called a midday depression in transpiration, because at midday there's a depression in the sap flow, in the water transpired by the tree. And this is a sign of heat stress. So in the model, we saw a heat stress situation, which we did not see in the measurements. And we suspect this is that in our model the roots did not get enough water, while in reality they do. It is a completely impervious surface, but it is very close to the Rhine River, and the Rhine River had different flows. It has been straightened in the past. So maybe it is getting water there. That is an assumption, yeah? And when we look at the leaf temperature, you see these two spikes as well. For the other periods, it's quite fine. And they, of course, they interact with each other. If the plant is not transpiring water, the latent heat flux goes down. So the temperatures are different. Yeah? So this is what you see in the results of the leaf temperature. So coming quickly to the conclusion outlook. We have a high agreement between model and measurement. But we have some idea now about a tree's health. Yeah? So we can say, okay, it is able to transpire X amount of water and thus have a beneficial effect onto the local microclimate. But what we have to tap more into the plant health. It's not just leaf temperature that determines a plant health. We also have to see dangers of mold. If a tree is situated into a place where ventilation is not always there, so then the water on top of the leaf, it might not get exchanged and evaporate. So the risk of mold is there. And if trees have enough ventilation or maybe have not enough water, some insects come and they destroy the tree. So having a risk assessment, this is something what we want. So wind, not just wind risk, but also insects of pesticides, yeah? And of course, determining on the wind field, we have quite recently, we had a lot of storms in winter in Germany, and many trees are falling, yeah? And maybe parts or branches of the tree or the whole tree falls. It is not just the cost of it falls into a car and the car is broken, yeah? This is also, of course, very important. But that the tree is damaged is a bigger cost, because it, again, takes maybe 20, 30 years until a new tree has the same size. So giving ideas of how to cut a tree correctly so that it is not so susceptible to being thrown down or damaged by wind is something as a risk assessment that makes a lot of sense. And we want, of course, more evaluation, yeah? This is something, other tree species. It was only London crane. I know there's a very cost-intensive research, but especially maybe here in the southern latitudes, in the tropics, yeah, the trees might behave completely different. So we have to think about, you remember the bubble diagram where we had the stomata behavior and so on and so on? So from a biological point of view, they are different. We need to cover this, yeah? We cannot be, we cannot pat ourselves on the shoulder, oh, we have it now and we explain everything. No, it's not the case. We need further research towards this. So as a conclusion for the two topics I showed you, they are linked with each other, yeah? So I talked about the building envelope. It makes a big difference to have each an individual facade. And if the trees is standing there, you see the shade. And the trees are not just shading, they're also having all the other benefits that we all know about, that we all want to ensure they keep our urban heat island to a minimum. And in a current project, we are also having a look at what do we do for alternatives in greening the city. And we are developing innovative smart living wall facades together with 5 private companies and 2 other universities. And in this project, our part is to develop an accurate representation of green roofs and green facades. And this is, of course, very important because even though we have a lot of money from the EU for this research project over 3 years, it's huge amounts, yeah? So we are able to put a lot of information, a lot of measurements, develop lots of different facade living walls and put them onto buildings in order to measure. You can never put it onto a bigger scale, being it maybe a city quarter. And the picture that I brought here, these are different types of green walls and they are being measured. And our part is now to first introduce these. This is already in the version of ENVI-met included, so that all the different radiation processes, latent heat fluxes are incorporated not only for a plant growing up a facade, but also for a living wall structure where the substrate is situated right next to the vegetation. And then we want to see, okay, in real life, in our multi-million euro project, we still don't have the money to put these different green facades everywhere and see, okay, what is not just the effect on the individual building, but on the city quarter. The thing I talked way in the beginning. You remember? Macro scale, meso scale, but we are on the micro scale. And this is something that we can change. So if it's not a single building with a green facade, but a city quarter, how does it change? And the model can give you a good idea. I think you remember this picture from the poster, yeah? And this is also the slide I want to close. And I sincerely want to thank all of you, and again, the work group of Professor Denis Duarte. Thank you very much.